I took this program that we were playing with and I modified it a little bit to make it more fun. I added this function called uWin. It just prints out uWin, but the point is it will never call it. Here's main. Main is going to call user input. User input is going to read into this buffer and just print the buffer that comes in and then return to main. It never calls this function. So I'm going to trick it into running this function even though the developer never tried to run that function. That's the plan. So I compile this thing there. I make 32-bit code with symbols called buff1, and it warns me that you really shouldn't be using the gets function. It's dangerous, which it is, because gets reads data from the user without any limit to the length. So you can put in more than you've reserved room for, and there's nothing to stop that. That's why you're not supposed to use it, but they don't stop you, they just warn you. And so now I can run it, and I can put in a long string like this, and then I get a segmentation fault. So now if I put it in the debugger, I can analyze what went wrong. Buff1, and now I can run it here, and put in that stuff. Oh, it's not listening yet, or I think it is listening. It doesn't have a prompt or anything. I should have said enter your data, but I didn't. So I put this in there, and now it crashes. And see, it crashed. This is what was in the instruction pointer, 4B, 4B, 4C, 4C. And that's not a valid address because that memory region was not reserved for this program. And so it crashed, and it doesn't tell you it's the EIP, but it is, and you can tell with info registers, it is EIP. Now you just need to know your ASCII. A is 41, then it's B, C, D, E, F, G, H, I, J is 50, and so B, so I got, all right, so 41, 4B and 4C, I could figure it out, but I'm not going to bother. I'm going to use my favorite page, which is ASCII table. All right, there it is. I go to this table. All right, so in hexadecimal, 41 is A, and what I have is 4B and 4C. So 4B is K and 4C is L. So I put in this string here, and the 32 bits that ended up in the EIP were those 32 bits. The last two Ks and the first two Ls. So now I know I can put in any value I want. Now the problem is, if I just type them in as letters, I can only use printable ASCII letters. And frequently I need an address that includes unprintable characters. So it's better to use a Python script. So I'm going to save this, and then I'm going to make a script. I'm going to nano exploit.py, import sys, then prefix equals, okay. Now I figured out it was the J's and K's, right?
2K and 2Ls?
I think it was the J's and K's. So let me save this. Okay. Now here's some rules. Okay, then I'm going to have EIP. I'm going to put in, say, XXXX here for now. Okay. Now, I think it was the prefix was up to, was the first two Ks, if I remember it right. Then I put in 4 more bytes, and after that come the Ls. And this, what I'm doing, is something you should always do. Keep your total length of input the same. Now this program is so simple it doesn't matter. But there are other programs we're going to use where you put in 1,000 and it crashes, you put in 2,000 and it crashes, but it crashed at a different point. So when you find a crash, you leave the length the same, so you keep hitting the same point, otherwise you will go mad. So now, if this works, the XXXX will end up in the pointer. I'm going to use bytes here because this is a way to print characters even if they're unprintable. In Python 3, you do sys write buffer. I've sort of forgotten this, just using it earlier today, but AI is good for it. Print sys There, I think the AI will figure it out. Yes, sys.out buffer right. That's what I wanted. I have trouble remembering that. Okay, that's the command there. And I can write prefix plus EIP plus, that should be suffix.
The second one.
Yeah, yeah. There. That's the idea. There. And so if I run that,
So you say the total length is the same, but you play around with the length of the prefix and suffix.
right, I put the X's here, so if it works, the X's will appear in there. So now I'm just going to run it in the debugger again. I guess I'll hit Control-C to get a clean line. Okay, GDB minus Q of buff1. All right, and now I'm going to run and take, okay, here, now let me do this better. The easier way to do this, Control-C, when I quit out of here, the best thing is put it in a file. I'm going to run Python exploit phi, and put it in, say, foo, there. Now I have this file called foo, which contains that data. Now I'm going to do the debugging. All right, get a clean line. Okay, there's the debugging. Now I can run and take the data from foo. And now it crashes with 58, 58, 58, 58. And that's good because 58 is X. The second column is hex. So 58 in hex is X. So the X's hit the EIP. So now I'm in control of the EIP. Now the question is, what do I want to put in there? And remember, that's why I put that win function in there. If I do a list, you'll see here's this win function sitting there. So I want to run that function. So I'll disassemble win. This is the address that starts the win function. So that's what I want to put in. I'm going to copy that. And I'm going to put that in my Python code. So I quit here. Yes, and now I nano my exploit. All right, and now I'm just going to put in a comment which has that in there. So I've got it. Okay, now that's what I want to put in EIP. And the way you do it, you have to put the characters in backwards byte order. So it is 9D, and you have to put a \x for hexadecimal, 9D, then 61, 55, 56. And it is very easy to get this wrong. So that's what I've done. You have to put the bytes in backwards order. 9D, 61, 55, 56. Like I say, we're going to get used to this little endian nonsense, but that's the way it is. So if I did it right, then that, if I run that and put that in my exploit file, foo, now if I run buff1, I take input from foo, I get UN. So we jumped, and we can do it in the debugger to make it more clear to see. If I go to the debugger and I list, I can do another list. Okay, here, let's put a breakpoint in line 17. Okay, and then a breakpoint in, actually, let's clear that. I just want to go to user input. I want to put a break before and after doing this. That would be good. Let's put a break at 10 and a break at 12. All right. And then I'm going to put a break at 5. There. All right, so now I can run it. And it's going to ask me for, I can run and take the data from exploit, from foo. There. And so it's going to run until it goes into this function and then stop in user input. I'm inside user input, but I haven't read the data yet. So I can do info registers. And I can see ESP is from B0 to D8. So if I X, say 16X ESP, remember the base of it is D8. So B0 goes to D8. There. That is the stack frame. That is the return pointer, 56, 55. The 56, that's what, so this is the stack frame of this function because I haven't read the data yet. Now I'm going to continue, and it's going to read the data. Now if I look at the stack frame, you see here's all these letters going in. A, B, B, C, C, 41 is A, 42 is B. And remember the return pointer was here. And now there's the return pointer. I've written it for this, and here's more letters coming, like I, J, K down here. So this is my exploit worked. I fed in that value, 5655, 619D. And if I disassemble win, I'll see that that address that I injected is equal to this address here. So now when it thinks it's returning to main, it's in fact jumping to win. So when I continue, now it prints, it's ready to print you win. It's in this, and so I continue again, and it prints the message. So that's the essence of buffer overflow exploit. That's the miracle that Aleph Null taught people, and all the viruses for like 20, 30 years have all been based on this pretty much. There's a few other tricks, but this is the main trick. So let me just see if there's anything else in the slides I wanted to mention. I think that's really the main point. Yep, we did all that, just a version of it. So here's the commands we used. It's worth doing. List shows source code. Disassemble shows assembly code. You run, we'll run the program normally. Break, inserts a breakpoint. X examines memory. Continue, resumes execution after you've hit a breakpoint. Info registers shows you the registers, and info proc mapping shows you the memory map. That's all you need to do what we're doing here. And GDB has 100 other features, but who cares? These are all the features we need. All right, so I got some cahoots about this. Yeah. Yeah.
You put a breakpoint at line X, line 5, so it means that line 5 is now run?
It runs to line 5 and stops before running it, yeah.
But now, okay, but then when you create 2 or 3 breakpoints,
yeah,
you need to give a continue in order for the first breakpoint to move on.
Yeah, and if you put a breakpoint inside a loop, it'll keep hitting it over and over. So
it moves by one.
Well, it moves until it hits that line again.
It's that line.
And if the line is in a loop, you might hit it many times.
Okay. So
yeah.
the breakpoint is the line run and then stop.
Yeah, before it runs that line, it stops. Yep.
Okay.
And we'll play with them. There's a lot of other ways you can do it, but yeah, good. This is the essential one here. So let me try a Kahoot. For chapter 2 of this class, let's see if I can get in. All right, good. Now I can sort them. Chapter 2, there we go. Hopefully I've been streaming. Oh, good. If I wasn't streaming, that would be highly unprofessional. Anyway, all right, good. All right, so what language causes these buffer overflows? All right, that's C, like I say, C and all its derivatives, C sharp and C++ and all that. All right, what memory section is the simplest to exploit with a buffer overflow? The stack buffer overflow is the normal one. The reason it's easiest to exploit is because you have those return pointers on the stack. So there's a nice handy target. Now you can take over the box with heap overflows, but it's a little trickier, and we will do it in the projects later. All right, so in this command, what is %x? That's a format string to specify what format you want to print the data in. It's going to turn out real important. We're going to get to format string vulnerabilities. C has so many mistakes you can make that ruin your life, and we'll see. That's why, I'm a fan of Rust. Anyway, all right. But C keeps us hackers in business. So, all right, so what register contains the address of the next instruction to be executed? The extended instruction pointer in 32-bit code, that's it. All right. All right, what register has the bottom of the stack frame? Sometimes called the frame pointer for that reason. Yep, EBP, the base pointer. All right. All right, what command shows the contents of the stack frame? This is the one that shows you the first 20 words. If it's a big stack frame, you might not get all of it, but this, you just have to change that number to get the rest of it. Shows you memory starting at ESP. That's the stack frame. This just shows you the size of the memory allocated to the stack, which will contain stack frames inside it. It doesn't show you any contents, though. It just shows you the start and end address of memory regions. All right, so what command shows C source code? List, but only if you compiled with the -G switch. If you didn't, it won't. And by the way, one fun thing I learned is it actually reads from the C file in the same directory. So I was able to make one with C code that was redacted, and you'll still see it in the debugger. Anyway, it's fun. It's very simple how it works. Anyway, let's see who was the winner. Tart. And so, all right, let me stop this recording and figure out